announcement for next week. The seminars will be on Tuesday from 1 till 3. That's simply because the ALT program will be using this run for the last 3 days. It's a pleasure to introduce Professor Richard Askey from Wisconsin-Madison, who will be talking on the world of Q and orthogonal polynomials.
Well, it's a great pleasure to be here. The last time I was in Cambridge, the Newton Institute didn't exist. In one of the buildings across the way, you can see the reason why I was here the previous time, which was to bring a bust of Srinivasa Ramanujan over and Robert Rankin was responsible for the plinth that it's on. Now, talks should start with something that's simple that everybody can understand. The world of Q really starts probably with Euler, but I want to start a little bit later than that. German mathematician, when he was young, Maximilian Stern, back in 1838, posed the following problem. You take the numbers 1, 2, 3, up to n. And he'd been reading Cramer's book on determinants, and so was aware that inversions were important. And so he asked the question, how many inversions are there in the permutations of 1 up to n? This is not that hard to solve, and it was solved a couple of times by Turkheim, and then Rodriguez published a paper where he gave a solution to that, but then he did more than that. He found the generating function for the number of inversions. And the generating function is 1 times 1 plus q up to 1 plus q to the n minus 1, which is a natural q analog of n factorial. Now, for the ordinary factorial, Leibniz asked the question, what's 1/2 factorial? And it was basically solved by Wallis in the work that he was doing. But Euler is the one who really solved it. And he had to work hard because you want a formula for n factorial that makes sense when n isn't an integer. And that's not so easy to do, but in this case, it's very easy to do. Any mathematician looking at that would replace this by 1 minus q to the n over 1 minus q, and then you work your way all the way back to that. And then if you take q between 0 and 1, you can put a tail on this, which you can't do with n factorial. And you get q infinity over q to the n plus 1 q infinity, 1 minus q to the 1 minus n plus 1, where a base q infinity is 1 minus aq on forever. What? Oh. It should be infinity. A base q sub n then is aq infinity over a q to the n. Q infinity. And I do it that way instead of as a finite product because later on we're going to be interested in it when n is a negative integer as well. And this formula makes perfectly good sense when n isn't an integer. So we have gamma q of x is q infinity over q to the x and q infinity 1 minus q to the 1 minus x. And it satisfies the functional equation. Gamma q of x plus 1 is 1 minus q to the x over 1 minus q gamma q of x. Now, in a school textbook, it was written by a couple of university professors in Denmark, Bohr and Mollerup. They finally solved the problem of how do you characterize the gamma function. There are many solutions to the functional equation gamma of x, f of x plus 1 is x f of x. And it was known that the gamma function doesn't satisfy any finite ordered differential equation. And what they showed is that if you have a function whose logarithm is convex on the interval 0 infinity, then it's a constant multiple of the gamma function. Fritz John, in a paper in ACTA around 1940, extended that to a wide class of things, which includes the Q gamma function. But there's another result that was done around 30 years ago, which you can motivate by gamma q of 1 is gamma q of 2 is 1, and they're both equal to gamma of 1 and gamma of 2. The graph of the gamma function looks like that. And here you would have value 2 for the gamma function, and you would have 1 plus q for the q gamma function. And this is clearly an increasing function of q on the integers. And what you can show is that gamma q of x is increasing in q for x bigger than 2 and x between 0 and 1, and decreasing for x between 1 and 2. Here I'm taking q between 0 and 1. It is possible to do a version of the q gamma function when q is bigger than 1. The Bohr-Molleroth theorem has to be refined a little bit. You go to the negative of the third derivative, or the second derivative being not just greater than logarithmic second derivative, being not greater than 0, but greater than some constant that shows up. And you can do this also. And my hope is that some people who are interested in functional equations will find some other functions that have monotonicity properties in a parameter like this. And the most natural one to look at is the beta function, which is gamma of x, gamma of y over gamma of x plus y. And then you can put a q version of that, gamma q of x, gamma q of y over gamma q of x plus y. In an earlier meeting site, I looked at this question, and I think I know what's happening. This is the point 1, 1, and 0, 0. You can prove that this function is an increasing function here. It's almost certainly increasing here also. You can show it's decreasing on these lines that are 1 unit apart in both directions because of the symmetry. And it's almost certainly decreasing in this whole region. And it's a sort of question that I'm still convinced that if I were 30 years younger, I could solve it. So I throw it out to some of you younger people who have the patience and the tools to do things like this. But what I would really like to have is classes of these equations. Fritz John found a class of functions for which there's an analog of the Bohr-Molleroth theorem. And we would like to have a corresponding class where you have a parameter and you have monotonicity in the parameters for various parts. So that's the first part of the talk, to convince you that sometimes the world of Q is nicer than the world of Q equals 1, because the Q gamma function was easier to come by than the gamma function. Now, many of you know that the world of Q is not always easier than the world of Q equals 1. But I want to show you another case where it is. And I'm going to pull an integral out of the air. This integral can be motivated either from orthogonal polynomials or from corresponding integrals that build up to it. And let me just record over here, a base q infinity is the product and goes from 0 to infinity, 1 minus a q to the n. And we're going to also use the fact that 1 minus a squared is 1 minus a times 1 plus a little bit later. And the integral we're interested in is this, and we'll consider right now a, b, c, and d and q being an absolute value less than 1. It doesn't have to be the case, and also consider them real. Otherwise, we take corresponding complex conjugates. This integral arose as the weight function for the most general class of orthogonal polynomials. It fits into what I would call the classical, or at least the neoclassic framework. The classical orthogonal polynomials of Jacobi, Laguerre, and Hermite satisfy second-order linear differential equations. The derivative of them is another class of orthogonal polynomials. Hermite goes into Hermite, Jacobi goes into Jacobi with the parameters shifted by 1. There are discrete versions of that where you use a finite difference operator. There's Q versions of it where you use the Q difference operator. F of x goes into f of qx minus f of x over qx minus x. And then there are the polynomials that have this as the weight function. Now this was worked out by Jim Wilson and Dick Askey quite a few years ago. The argument here was due to, that was in the memoir that Jim and I wrote, was due to Jim. He had earlier worked out a corresponding integral, gamma of a plus ix, gamma of b plus ix, gamma of c plus ix, gamma of d plus ix, over gamma of 2ix, modulus squared dx. And he'd done it using Cauchy's theorem. And you end up with 4 infinite series that you can sum, and then you have to put these things together. And there's common factors that come out, and then you're left with gamma of a times gamma of 1 minus a is pi over sine pi a. And corresponding things like that, and you have a really complicated trigonometric identity in 4 variables that you have to prove. It's clearly the wrong way to do this because the final answer turns out to be very nice. And worse than that, there were conditions that had to be put on the parameters so that the integrals are going to converge, and then you get rid of that by analytic continuation later on. And the same argument sort of works here. You can use Cauchy's theorem, and you get 4 series that you can sum, and then you have a mess that you have to deal with. And so the question is, what's Q trigonometry? And the answer is Q trigonometry is elliptic functions. And it turns out that it's easier in the Q case to do this because you can show that the function that you have has at most 1 pole in a period parallelogram. Therefore, it has to be a constant. And then you can identify the constant, and then you can, by analytic continuation, get rid of things. But there ought to be a better way of doing this integral. And there are, and here's my favorite. Let's turn this into an integral involving x is cosine theta. So h of x and a is going to be the product 1 minus 2ax q to the n plus a squared q to the 2n. This is a e to the I theta, q infinity, a e to the minus I theta, q infinity. When you multiply these things out pairwise and use Euler's formula for the exponential. So we're interested now in this integral. have down below h of x and a, h of x and b, h of x and c, h of x and d. Up top, cosine 2 theta is twice cosine theta minus 1. So this is h of 2x squared minus 1. And then it's dx over square root of 1 minus x squared for the d theta. So we want to see how to do this integral. And what we would like to do is to set up a functional equation and then iterate. And so let's look at 1 over h of x and aq, h of x and b, minus 1 over h of x and a, h of x and bq. And that's h of x and a, h of x and b. And you have 1 minus 2ax plus a squared minus 1 minus 2bx plus b squared, which isn't good enough because you don't want that x there, but you can get rid of the x by multiplying the second one by a and the first one by b. And what you get is b minus a times 1 minus ab, h of x and a, h of x and b. Well, that suggests that you ought to be looking for the value of this integral as a function of a times b. It's clearly symmetric in a and b. So let's see what would happen if we took this thing to be f of ab, f of ac, f of ad, f of bc, f of bd, f of cd. And basically use this functional equation right here, because you can just integrate this stuff right here with respect to the rest of this measure. And what you get, I think I'll save a little time by just writing out what you actually get. Well, if we call this I of A, B, C, and D, what you have is B I of AQ, B, C, D minus A I of A, B, Q, C, D. Turns out to be B minus A times 1 minus AB times 1 minus AB. No, let me do this thing out. Should never skip steps. You end up with B minus A f of or I of A, Q, B, C, D minus A of I, A, B, Q, C, D. Equals B minus A, 1 minus AB, I of A, B, C, D. And then if you guess that this is going to be this thing, you end up with B f of ABQ, ACQ, ADQ, f of BC, f of BD, f of CD, minus the corresponding thing with the B now shifted. Equals B minus A times 1 minus AB, f of AB, and so on.
Sorry, Dick, is the first term in the brackets there, should that be B? The first line? Oh, yeah, that one.
Yeah, that should be B. Thanks. And then what you do is you take C equals D equals 0, and you get B minus A, f of ABQ is B minus A, 1 minus AB, f of AB. And both sides have f of 0 to the 5th power. That goes out. And that gives you f of AB is f of ABQ divided by 1 minus AB. And so what you get is f of AB is going to be f of 0 over AB base Q infinity. Now that's what f has to be if the value of this integral is of this form. So you put this in, and it turns out it doesn't work. What you end up with is a factor 1 minus ABCD on one side and not on the other side. And therefore, you have to go back and throw in another factor that's a factor of the product of the 4. And then you do the same thing. You throw that in, you set C and D equal to 0 again, and you end up with the following. The same sort of functional equation. So you get I of AB, CD is AB, CD, Q infinity over AB, Q infinity up to CD, Q infinity. And then there's some function of Q. And this, in fact, satisfies the functional equation. And then this thing up top, h of 2x squared minus 1, is h of x and q, or h of x and 1, h of x and q to the 1/2, h of minus x, h of x and minus 1, and h of x minus q to the 1/2. Just using this fact and then sieving and looking at every other factor. And so you can reduce the integral to a triviality by taking a equals 1, b equals q to the 1/2, c is minus 1, and d is minus q to the 1/2. And when you do that, you get q infinity down below here, and you get a factor of 2 pi. And that's the value of this integral whenever you can do the iteration from initial values. So you need a couple of initial values to work out. We've worked out one of them already by this choice. 1 minus q to the 1/2 minus 1 q to the minus 1/2. You can take q and q to the 1/2 minus 1 and minus q to the 1/2 and get another trivial integral to do. And it turns out it's the correct value. And then with iteration through A and B, and then the symmetry in C and D, you have that this is the value for infinitely many values of A, B, C, and D. And each of them has 0 as a limit point, and it's analytic in those variables, and so you have it in general. Now, the amazing thing is that this proof isn't like any of the valuations that I know of the gamma function. And I don't really remember how I came up with it. Because what do? You think about the ways of evaluating a beta function and try to see where any of them will work. And, well, setting up a double integral doesn't look particularly hopeful. Differentiating using integration by parts doesn't look very helpful. Another way that you can do the gamma function is to turn it into an interval like this, and then throw a constant c in there, and then differentiate with respect to c. And that doesn't look helpful, but that's the closest you can get to it. But to throw that factor in, you have to use the fact that the interval 0 infinity remains fixed when you change variables. And that doesn't happen in this Q case with the integration variable. It does happen with the parameters. Okay. Now, once we have the value of this integral, we have a lot of freedom in the parameters that we have. And we can get the orthogonality for the following class of polynomials. Wn of x, a, b, c, and d is q. X is cosine theta. This is the sum. K goes from 0 to n. Q to the minus n is qk. Q to the n minus 1, a, b, c, d is qk. A e to the I theta, qk. A e to the minus I theta, qk, times q to the k, divided by qk, ab base q sub k, ac base q sub k, ad base q sub k. And if you throw in the appropriate factors out front, this function becomes symmetric in the variables a, b, c, and d, as the weight function is symmetric, and that gives you transformation formulas. Now, one formula that we can get from these polynomials with the orthogonality is what happens when you change variables. And so we'll get some coefficients, alpha, well, say f of k and n, wk of x, alpha, beta, gamma, and delta. And the question is, what are these coefficients? Well, if you shift only one of the parameters, keep 3 of them the same, you can find these coefficients explicitly, and I'll give you the formula for that in a minute. Once you have one of these, then you can iterate with it. So to shift 2 of the parameters, you get the coefficients as a single sum. And then iterating, shift 3 of the parameters, you get it as a double sum. Shift 4 of them, you get it as a triple sum. Except when you do this directly, when you shift 3 of the parameters, this turns out to be a single sum. Well, I don't know how important that miracle is, because nobody's used it yet. So at present, it seems to be a minor miracle. But when miracles exist, even if they're minor ones, there's got to be a good reason for it. let me write down what the formula is in the case where you shift just one of them. This is a formula found by G.N. Watson. It's an extension to the basic hypergeometric functions of a formula found by Whipple. So this is really an old English subject. L.J. Rogers had some pieces of this also, as did Ramanujan. K goes from 0 to n, q to the minus n. I'll leave off the k, aq over bc, d k, e sub k, q to the k over q, k, de, q to the minus n over a sub k, aq over b sub k, aq over c sub k is aq over d sub k sub n, aq over e sub n. Bear with me, it doesn't go on forever. But I have to have the whole thing up. And this is a miracle also. And I want to show you two reasons why it's a miracle. The first why it's a miracle, and second why it's a major miracle. Hypergeometric series or series summation an, where an plus 1 over an is a rational function of n. The basic hypergeometric series, the term ratio is a rational function of q to the n. Hypergeometric series starts with a binomial theorem. 1 minus x to the minus a is the sum a sub n over n factorial x to the n, where here a sub n is a plus 1 up to a plus n minus 1. This has often been called a Pochhammer symbol, but Pochhammer didn't use this notation. And I like to call it just a shifted factorial. It's just n factorial, but you shift from 1 out to a. And part of the theory of hypergeometric functions starts with one minus x to the minus a times 1 minus x to the minus b is 1 minus x to the minus a minus b. And you look at the coefficient of x to the n on both sides. In one case, it's a sum. In the other case, it's just a product. That's the first of the results for hypergeometric functions. It's equivalent to this. It's often called Vandermon's convolution. If you write it in the form that you would get when you took the Cauchy product of those series, it's equivalent to this form. Gauss looked at the non-terminating case of this and summed the series. And then you go on from there. And you can work your way up quite a ways. The other one starts with 1 minus x to the minus a times 1 plus x to the minus a is 1 minus x squared to the minus a. Now that's a completely different formula than the other one. And this turns out to give you the sum of that series. A sub k, b sub k divided by a plus 1 minus b sub k, k factorial. And what's happening here is that there's an implied 1 down below from the k factorial, and this a plus 1 and a plus 1 minus b plus b are the same. These are called well-poised series. When you get one step above this, the series that you can actually sum, the sum of the numerator parameters plus 1 is the sum of the denominator parameters. These have been called Salschutzian. Salschutz found it, but Pfaff had it well before Salschutz. I call them balanced series. You balance the bottom and the top, and sometimes you want to sum by 2 rather than by 1. Balanced series are these. These are well poised. Here, the product, there's a Q here, AQ, 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 and so on, all the way down. The connection between balanced series and well-poised series ties up these two totally different types of characters. And that's a miracle. There's no reason why those two should be tied up. And this is the minimal level where they're tied up at the right level. And to show that that's the case, that it's a miracle, let me remind you of the Rogers-Ramanujan identities. There are two of them. The sum n goes from 0 to infinity, q to the n squared over 1, or qn is q base q to the 5th infinity, q to the 4th, base q to the 5th infinity. And the other one, q to the n squared plus n over qn, is 1 over q squared, q to the 5th infinity, q cubed, q to the 5th infinity. Now, for each of these, we can put in the missing factors. We're missing the powers of q that are congruent to 2 mod 5, 3 mod 5, and 0 mod 5. So we put them all in, and we get q infinity down below, and q squared, q to the 5th infinity, q cubed, q to the 5th infinity, q to the 5th, q to the 5th infinity. And this is just a special case of a theta function. And let me write down Ramanujan's extension of the theta function. As one case where I can show you where these quadratic powers come from. A base q sub n over b base q sub n, x to the n, is, now I've got to write this down in the right order, or I won't get it right. This converges in the annulus when the absolute value of x is less than 1 and b over ax is less than 1, so x is there. To show that this contains the triple product for the theta function, you take b equals 0. That wipes that out, this out, this out, and this out. You replace x by x over a. And then you let a go to infinity. And on the left-hand side, you get the sum minus 1 to the n, q to the n times n minus 1 over 2, x to the n. And on the right-hand side, you get x q infinity, q over x, q infinity, q infinity. Every time you have a quadratic power of q, when you're looking at it the way I look at it, you want to get rid of it. Which means that I'm not interested in the modular aspects of these things. I'm interested in things that tie up with combinatorics, things that tie up with orthogonal polynomials, and all sorts of other things. Now, you use the triple product on that thing up top. You get minus 1 to the n, q to the 5, n times n minus 1 over 2 from the q to the 5th. And you get q to the 2n from the q squared there. The 2 and 3 have to add up to the 5 to get a triple product. So we should have 5 free parameters for one of the Rogers-Ramanujan identities. And there are 2 of them, so there should be a 6th parameter. That formula of Watson has exactly 6 parameters. Now, you can take that formula and extend it. And one way of extending it has been worked out, and you get Rogers-Ramanujan identities to moduli that are bigger than 5. Multiple sums on one side and going up with higher hypergeometric functions on the other side, single sums still. Basil Gordon was the first person to get this. He didn't do it quite that way. George Andrews did do it that way, eventually. The thing that Wilson and I had can be iterated the other direction. So moving the other series up among the hypergeometric functions and getting multiple sums on the other side. We don't know yet what that's going to lead to. And then, of course, you could bifurcate, and you could go up partly one chain, partly the other chain, and then work your way up. It's a potential gold mine if somebody can figure out what to get from it. Because there's a machine that's already built that will do these things for you. Okay, now, I want to say just a little bit about some special cases of those polynomials, those 4-3 polynomials. The first person to make a really big breakthrough in this area was L.J. Rogers. And he found a set of polynomials that satisfy the following recurrence relation. 2 times 1 minus beta q to the n x cn x beta q is 1 minus q to the n plus 1 cn plus 1 x beta q plus 1 minus beta squared q to the n minus 1 cn minus 1 x beta q. These things come from the polynomials that we had before, from a q to the 1/2 minus a, and minus a q to the 1/2, where a squared is beta. And Rogers found a number of formulas for these polynomials. One of them was Cnx gamma q is the sum of a, k, n, c, n minus 2k, x, beta, q. I use a bar here rather than dots because the measure is absolutely continuous. I've never explained in print why I use a bar for some of these things and dots for the others, but others have discrete measures. And these coefficients are just products of the q shifted factorials. The corresponding thing in the case q equals 1 was one of the things that Gasper and I used to prove a certain inequality that ended up being the final step in de Branche's proof of the Bieberbach conjecture, which we'd done 10 years earlier from some positive quadrature methods that had suggested certain inequalities. And then there's this formula, where there still is no really nice proof. It take the product of two of these and you write it as a sum. And again, the coefficients are products, quotients of these Q-shifted factorials. This is a formula which was done by Rogers. For the case of Legendre polynomials, it was done by Adams. And he said the way he did it was to work out what happens for the first 5-degree polynomials multiplied by Pn, see a pattern, then prove it by induction. Neumann came up with a nice way of proving that from differential equations. He got the differential equation satisfied by the product and then linearized it. But that one just smells of algebra, an algebraic treatment of special functions. And every time there's a new book out doing special functions from an algebraic point of view, the first thing I look at is to see how they did that. And nobody does it that way. The Legendre polynomial one you can do that way, and the Chebyshev polynomials are the first and second kind. First kind is trivial, and the second kind does show up in some of the algebra work. But this isn't the thing that shows up in the algebraic treatment of special functions. Parameters shift there. Now, what can you do? You can take that weight function that I've erased, and you can let q equal 0. Who would ever believe you could do anything interesting in a q series when q is 0? But the polynomials that you get turn out to be orthogonal with respect to this measure. 1 minus 2ax plus a squared, 1 minus 2bx plus b squared, 1 minus 2cx plus c squared, 1 minus 2dx plus d squared. Special cases of these were, well, more general ones were actually studied by Bernstein back in the 30s. But he didn't use the right notation, and he tried to go beyond 4. And the formulas don't get so nice after 4. They're nice because of this. The corresponding integral there is in Littlewood's book on group characters with the 4 degrees of freedom. And he uses it in some of his work on some of the classical groups, which suggests that the Q thing ought to show up in corresponding things. Cartier came across some special cases of these polynomials and spherical functions on trees. So that's one thing you can do. And the formulas that you get would not be easy to come up with. You can write down the polynomials as the sum of Chebyshev polynomials of the first, second, third, of the second kind, with various symmetric functions showing up as coefficients. But the linearization and the connection coefficients, you'd be hard pressed to do them directly from that. But in the Q case, it's easy to see what is happening. You don't only have to go up through n equals 2 to get a pattern, which is probably what Rogers did and then proved it by induction. He didn't say how he did it, he did just prove it by induction. But then you can let Q be a root of unity. And the weight function turns out to be uk of x to a power, and then 1 minus x to the lambda plus or minus a half, 1 plus x to the lambda plus or minus a half, and you can take them independently. And you can do it with a slightly larger class than this, with 2 parameters, and you get the product of 2 different Chebyshev polynomials. And so what you have then is weight functions that have zeros on the inside. The recurrence coefficients that all orthogonal polynomials satisfy turn out to be sieved in these cases. So they're zeros, they're constants except along a certain arithmetic progression. With 2 parameters, you can get 2 different arithmetic progressions. The only case we knew about that before this was q equals -1, when you had the polynomials that are orthogonal with respect to 1 minus x squared to a power times the absolute value of x to a power. That's in Sego's book on orthogonal polynomials. And having these examples opened up the general theory of orthogonal polynomials to try to find out what was really happening with interior zeros. Because before that, you basically had to deal with weight functions that were strictly positive in an interval. In Sego's class, you had ones where the logarithm of the weight function was integrable. So, are there any operators here? And the answer is yes. And let me just take 2 minutes and tell you what the operators are. There's d by dx for the classical polynomials. There's f of x plus 1 minus f of x. There's f of qx minus f of x over qx minus x. You can look at the polynomials that are orthogonal with respect to absolute value of x to a power times 1 minus x squared to a power. And there you have polynomials of degree n in x squared. And the way to cut the degree down is to differentiate and then divide by x. You have those polynomials that I mentioned in the hypergeometric case that Wilson had, where they had the weight function a plus ix, a minus ix. They have an a plus ix sub k, a minus ix sub k. And that's basically quadratic. And what you look at there is f of x plus I over 2 minus that divided difference operator. And that's the operator that acts on those polynomials. And for the ones that I've been talking about here, they're orthogonal on -1, 1. You project up to the circle. You go out like that, and you take q to the 1/2 e to the I theta and q to the -1/2 e to the I theta, and use the divided difference operator there. Alphonse Magnus, in a meeting in Bar-le-Duc, the first of a long series now of orthogonal polynomials, showed that sort of a non-symmetric version of that is the most general operator of a certain type that has the properties that you want to have for acting on polynomials. And you can symmetrize things, and so in some sense this is the most general operator. But that isn't the end. This is probably the end of the classical orthogonal polynomials in one variable. But you can get rid of the restriction that you have classical, and there are all sorts of other ones that show up with nice recurrence relations that don't satisfy this. Felix Polacek made the first major discoveries there. And you can relax the fact that you're working with orthogonal polynomials and work with orthogonal rational functions. And you can go one step higher in the category of hypergeometric functions and basic hypergeometric functions and get biorthogonal rational functions. And then you can go beyond basic hypergeometric functions to the elliptic hypergeometric functions, which is a fascinating field that I wish I were 30 years younger. And not so involved in the other job that I'm working on right now, which is trying to see whether we can get some mathematics back in school mathematics. There you don't have these two families, you only have the well-poised family. For reasons I still don't understand, but I'm willing to believe it. And then you can go to several variables, and in several variables there are many, many different ways of doing it. the polynomials that I've talked about in the q equals 1 case, where you don't have the absolutely continuous measure, but you have just a purely discrete measure, turn out to be the 6j symbols in angular momentum theory. The ones below that are the 3j symbols, and then you go to the 9j symbols. And they're orthogonal polynomials in 2 variables if you learn how to do the transformations. One would like to think that they would be double series. The best anybody's found so far is a triple series representation for them. And one hopes that there is something. I'm getting less and less optimistic about that because some good people have tried. But you young people should realize that when a senior mathematician says there's something to look at in a certain area, take them seriously, because they usually have the right intuition. But if they tell you that there isn't something there, feel free to ignore them somewhat. All they're saying is that they don't see what there could be. And I've been wrong, and all sorts of great mathematicians have been wrong in the way that they have misled generations of things that they thought were dead ends that weren't. When I was young, I don't know how many people told me that the subject that I was working with was dead. Why are you doing it? Well, I was doing it because I was led from certain problems that I was doing to some places where there were results that weren't known. So I had to learn all this classical stuff myself. And it turned out to be a gold mine, as you see. I mean, some of this stuff I did. I didn't do all of it at all, but some of it did. And so don't take the pessimism of the senior generation too seriously. But when they tell you to look at a problem, there are probably some good reasons why you ought to look at it. So.
You mentioned that for the 9j case that you think it can come down from a triple product representation?
I would hope that it might, but I'm getting less optimistic of it.
Why would you think that it might?
Well, orthogonal polynomials in 2 variables should be given as double sums. I mean, the 6j symbols were initially 4 quadruple sum. That's what Wigner got from the group theory. And Raka showed how you could complexify that and then simplify it step by step and get it down to a single sum. And it's when you have a single sum that it really is useful. And that explains what's really happening. And so one would hope that that would carry on through the hierarchy. I mean, there's all this stuff with McDonald, Kornlander, and other people in different ways of looking at several variables. And we don't know yet whether these completely bifurcate or whether they will get together at another level. The Gelfand stuff is another example. So, I mean, it's a very exciting field now. So, other questions?
So let's ask you again.